So today we're going to be talking about trends, more specifically trends that occur and trends that we can see within the periodic table. So within the periodic table, it may seem that they are just random elements, but they actually have a very strict pattern, and through this pattern we can gather a lot of information such as atomic radius, ionization energy, and electronegativity, and one more thing that we'll cover later. So first of all, taking a look at atomic or ionic radius, and this just means the radius of an atom, and the radius of an atom is calculated by the distance from the atomic nucleus to the farthest electron in the atom. And this generally shows how big an atom is overall. And there are two main types of radiuses that we must consider. First of all, atomic radius, and second of all, ionic radius. And the difference is that the atomic radius is measuring the radius of a neutral atom, and the ionic radius is the measurement of a radius of an ion. And for atomic radius, for basically atoms that don't have a charge of positive or negative, the way we see which atoms have a bigger atomic radius is by looking at the periodic trend. And the periodic trend for atomic radiuses is that the lower bottom corner of the periodic table are generally has a bigger radius. So it kind of goes like this. So as it goes down and as it goes left, the atomic radius of atoms are increased. So we can generally think of it like this. And the atoms in this area would have the largest atomic radius, and the atoms in this area would have the least atomic radius. So when we are comparing two atoms to see which one has a bigger atomic radius, we have to see which one is closer to the bottom left corner of the periodic table. So let's say we are comparing nitrogen and boron. Now, since the trend is in such fashion, boron would obviously be the atom with the bigger atomic radius because it is more left than nitrogen in the periodic table. Another example would be iron and tungsten. Now, as the periodic trend is in such fashion, remembering that it goes larger as it goes left and bottom, we can see that tungsten would have the bigger atomic radius. Now, you might be wondering, what if we are comparing lithium and magnesium? Now, this is a bit more complicated because although the trend is in such fashion, which one is prioritized, the one in the bottom or the one on the left? Because the periodic trend is that as atoms are lower in the periodic table and more in the left side, the atomic radius is greater. But which one is prioritized? And in every case, the one in the bottom is prioritized. So the bottom aspect is way more important than the latter. That is how we compare atomic radiuses. And for ionic radiuses, it's slightly different. And ionic radius, ions generally have more or less electrons. And the way we compare two different ions, we first of all have to consider the number of protons they have and the number of electrons they have. So due to the fact that protons pull in electrons, atoms with a higher number of protons have a lower atomic radius, and atoms with more electrons have a greater atomic radius due to the fact that electrons cause repulsion with each other and make the atom's radius bigger. Now that was all for atomic and ionic radiuses. Now moving on to ionization energy. Ionization energy can be defined quite simply by the energy that is required to remove an electron from a gaseous atom, so a gas type atom. Not liquid nor solid would work, only gas. And basically successive ionization energy is how much energy it requires for specific electrons to be removed. So for example, and also the successive ion energy is often denoted as IE for more simplification. Now, to remove this electron, let's say that the energy IE is 1 because it's the first one. Now, to remove this electron, let's say that the energy is IE2. But then what happens with ionization energy is that electrons that are removed Now, the thing with ionization energy is that when an electron of the shell, so the thing with ionization energy is that if an electron is the last electron in that electron shell or orbit, it has the greatest ionization energy. So because this electron is the last electron in its shell of N2, it would have a bigger ionization energy than the one right over here, because there is also another electron right over here, and it shows that it is not the last electron in its shell. So that is how ionization energy works. And ionization energy, when comparing more than one atoms, can also have a periodic trait, but it is opposite from the atomic/ionic radius. It actually goes bigger as it goes higher and to the right. Now for this, also height is prioritized, so if we were to compare zinc with let's say aluminum, zinc would have the bigger ionization energy because it is higher, although indium is more right. Height is prioritized within the periodic table. Now going to one of our second last topic of electronegativity. Electronegativity is defined as the relative ability of an atom to attract shared electrons to itself. So it basically means the amount of energy that an atom has to pull electrons to itself. So it's basically the power to pull electrons to oneself. And the trend in the periodic table is same as the ionization energy, as electronegativity becomes greater as it goes right and to the top of the periodic table. Now, one thing to mention is that for when considering ionization energy and electronegativity, the last column of noble gases are not considered due to the fact that noble gases have a full electron shell of 2 or 8. They are not very active and they do not want to bond because their valence electrons are already 2 and 8 or 2, already full and very stable, so they are not very reactive, and these noble gases are not counted and not considered when talking about ionization energy or electronegativity due to the fact that they do not bond with each other. So noble gases aren't considered. And so there are three main periodic trends that you must know. Oh, also another exception is that for the atom Xe is actually the only noble gas that is considered for electronegativity, and that's a bit of an exception that you don't need to memorize, but it's good to have in mind. Now, these three are the main trends in the periodic table, periodic trends. But there is actually one more slight minor trend called electronegativity. Electronegativity. And what electronegativity basically means that called Electron Affinity. And what basically electron affinity is that it is the energy that is required, or the energy change when a gaseous atom gains an electron. So it's basically quite opposite from ionization energy. Ionization energy is the energy that is emitted when an electron is lost from an atom. And electron affinity is the energy that is absorbed when, or the change of energy when a gaseous atom receives an electron. And the very general periodic trend for electron affinity is similar as ionization energy and electronegativity. It goes up. The electron affinity becomes higher as atoms move towards the right and towards the up. But for electron affinity, it's slightly an exception because not all atoms work with this atomic trend or this periodic trend. This is just a very general way of how it works, and there are a lot of exceptions to this periodic trend, so don't rely on periodic trends for finding out electron affinity too much. And that sums up the 4 main trends within the periodic table.